Millions of lives are saved by antibiotics. From treating common infections to allowing organ transplants, antibiotics have extended average lifespans by decades.
No intensive care. You wouldn't have any intensive care if it weren't for antibiotics. So they're absolutely revolutionary.
But have we been too clever for our own good?
Each year, about half of the emergency cases treated in this intensive care unit are suffering from bacterial infections or sepsis. The problem is they're starting to see infections they can no longer treat.
Bacteria are rapidly becoming resistant to all the antibiotics we have. By overusing this precious medical resource, we risk losing the potency of antibiotics forever.
This is one of the most serious threats to human health. Without antibiotics, we could end up in meltdown.
Even the way we produce food adds to the resistance backlash.
We've got to change the thinking as a community, and we've also got to change the thinking of farmers that, they can't think of antibiotics as an easy fix.
To combat resistance, new science sees ourselves as part of a much deeper bacterial ecosystem.
Part of the problem, I think, is we've seen bacteria in the same way we see a cockroach. We blame a bug, we give it a name, we try and stamp on it like a cockroach.
We're locked in an arms race with microbes. On the one hand, we've been spilling antibiotics into the ecosystem for decades. On the other, bacteria have an infinite capacity to adapt. If we're going to win this fight, then we need to be much more sophisticated.
As an ecologist, I tend to see everything as interconnected. And that's my starting point to explore this threat of antibiotic resistance. Bacteria are everywhere. We're an integral part of their invisible ecosystem.
Everything you look at, everything you touch, everything you pop into your mouth is covered with millions and millions of bacteria.
These swabs should offer some insight into my own bacterial environment, though I'm not sure how much insight I really want. Coexisting with bacteria makes human life possible.
I think the cherry ones are much more tastier than the big ones.
Okay.
Without them, we couldn't even digest our food properly.
Living harmoniously with them is the key to a healthy lifestyle, both at an individual level and on a global scale.
But many species can become pathogenic.
We know that 1 in 3 Australians before 1930 died from an infection. And of course, for young kids between the ages of 0 and 5, many kids got an infection early in life and wouldn't make it beyond it.
So when antibiotics were developed in the 1940s, they promised a medical revolution. Previously lethal infections could now be simply and effectively treated.
Almost half of the people on the planet died from an infection before antibiotics. So it's changed human health. After clean water and sanitation, it's probably the most amazing discovery we've made.
But there's an essential paradox in the power of antibiotics. The more we use them, the less effective they become. And here's why.
In soil, water, animals and plants, wherever bacteria live, they naturally develop resistance. They've been at it for more than 3 billion years. It's all about survival.
Over these billions of years, they've evolved all these mechanisms to try and combat each other. So they've been doing this kind of chemical warfare where they're all battling against each other, trying to create a niche to survive.
And in the last microsecond of geological time, we provided a new stress, which we call antibiotics, which we think we're very clever about, and they've adapted to that very effectively as they've adapted to everything else.
When our antibiotics don't kill all the pathogenic bacteria, this selection pressure ends up skewing their populations to become more resistant.
Some bacteria can replicate in 20 minutes, whereas it takes us 20 years to get to that stage. So bacteria can evolve resistance very quickly. They also love to have sex.
But more than that, bacteria can share genetic material without the need for sex. And that's the key to their stunning ability to rapidly adapt. We're all born with a set of fixed genetic traits, like eye colour, that don't change throughout our lives. My daughter Jess has blue eyes, and blue they'll be forever. Not so bacteria. Some microbes, like the gut bug E. coli, share genetic material by just being close to one another. They exchange bits of extra DNA, such as resistance genes, in packages called plasmids. Proximity is all that's required. It'd be like Jess changing her eye colour just by standing next to someone. It means resistance can be passed between bacteria at astonishing speed, as Dr. John Iredell witnessed in an intensive care patient being treated with antibiotics for an E. coli infection.
Next day, when another blood test was being taken, that little E. coli grew again in the blood, but had acquired that genetic package that it needed to resist the antibiotics that had been used the day before.
That rate of change has taken us by surprise.
What we've underestimated is the speed at which this has arisen. And so a problem we thought we'd have in 100 years' time or longer is now coming right up at it. It's a train, a freight train coming down the tunnel, and we can see the lights there.
Over the last few decades, the number of new antibacterial classes has declined, while the amount of resistance has increased. For example, the antibiotic ceftaroline was introduced in 2010. By the very next year, resistance was detected. Australians are among the highest users of antibiotics in the developed world. Dr. Kate Cleese is working to reduce the astounding 30 million prescriptions for antibiotics dispensed annually in Australia. That's more than one script for every man, woman and child every year.
What I would recommend to the team was that if the cultures come back negative, then I would stop that. But we're still waiting on some of those results. There's been a lot of studies that show maybe 40 to 50% of antibiotic use in hospitals is unnecessary. If we overuse those antibiotics and resistance develops, then there's a whole lot of areas of medicine that would be very difficult to continue with. So it's really important that we make sure in hospitals like this that we have a message about using antibiotics appropriately.
We need them now more than ever before. So they remain a fantastic weapon. We think that probably the antibiotic intervention is one of the most powerful interventions still in modern medicine. And so it's essential that we preserve that capacity.
But for something so valuable, many of those prescriptions for antibiotics are wasted, or worse still, used when they'll never work. Too often, when we have the sniffles, we reach for an antibiotic to treat a viral infection. But antibiotics don't work on viruses.
We want to kill whatever bugs we can kill, whatever pills we can get our hands on. And this is obviously a message that I think the public are increasingly aware of as problematic.
As resistance spreads, hospitals face a crisis.
I think the cleaning department is on the front line.
These basic principles we need to revisit and say, look, are we doing these basic things? Hand hygiene, hospital cleaning, hospital design. Is there one bum per toilet? All new hospitals should be only single rooms.
A global health catastrophe is looming. The problem of antimicrobial resistance currently kills 700,000 people worldwide every year. That figure is forecast to explode to 10 million by 2050. Although human use is the major contributor to the problem, our food production systems also play a big part.
Intensive farming practices in many ways have only been possible because of the increased and really inappropriate use of antibiotics, where you've got millions of chickens on a 1 acre lot, stacked one above the other, the top lot defecating on those below them, and the spread of organisms is massive.
In Australia, 70% of the antibiotics we use are on animals. That statistic infers excessive use, but experts like Mary Barton say that's not the case in this country.
I've mostly worked with pig and poultry, and in poultry, I mean, despite all the mythology about the tons of antibiotics being fed to chickens, it's a total myth. And in fact, a very restricted range of antibiotics that can be fed, for example, to, well, all chickens, but egg layers in particular. Pigs, there are a few issues in pigs, but I think the pig industry is really taking a very positive approach.
It's inevitable that growing large numbers of animals in confined spaces like feedlots creates an environment in which disease and resistance spreads easily.
If we live in a world of bacteria, how would you describe a piggery?
Just like a hospital.
A hospital?
Well, you've got lots of patients in a hospital, you've got lots of pigs in a piggery, and close contacts as organisms spread between the patients and the animals, or between the things that are in the environment of the hospital and the piggery.
Australian pig farmers are adopting alternatives to antibiotics like vaccines, modifying feed and improving infection control.
And what are the implications then for developing antibiotic resistance?
Well, if you use less antibiotics, you take the selection pressure off, and so the resistance will emerge more slowly. It's never going to stop it, but it'll be slower.
But even when we reduce use in Australia, the big problems are coming from overseas.
We know that there's a very tight link between the tonnage, not milligrams as in human, but tonnage of antibiotics used in agriculture and the emergence of resistance.
And some bacteria are better at developing resistance than others. Gram-negative bacteria, such as E. coli, are adept at transferring resistance not only between themselves, but across species. Microbiologist Alicia Elliott has been taking a close look at the swab samples from my home.
On your toilet door, we found a bunch of different microbes. Perhaps we have 2 different strains on here, or 2 different bacteria.
And then you compare it to the mobile phone.
Which is this one here.
Oh, no.
And what do you think?
I think they look a little too similar for my
Yes, a
liking.
little too similar. So we did microscopy on these and gram staining, so I can confirm that they are gram-negative species.
So that means that microbes I pick up in the bathroom are being transferred to the phone screen.
Very potentially, yes. And then...
While Alicia assures me that my household bacteria are normal, there's plenty that could turn nasty. On my phone and toilet door is Acinetobacter. In the soil is Klebsiella. Both have multiple drug-resistant strains that cause outbreaks in hospitals.
Could any of these be superbugs though?
Yes, certainly any of these bacteria have the potential to pick up resistance and then become superbugs.
So, we live in one big microbial soup. As long as bacteria have the right conditions, they don't care where they live. Which means bacteria and their resistance genes get passed between humans, between animals, and between humans and animals.
I think they're pleased to see us.
Take the travels of a superbug called methicillin-resistant Staphylococcus aureus, or MRSA.
Horses carry a horse-adapted strain of methicillin-resistant Staph aureus, which came originally from humans, but it's become adapted to horses. But that spreads back to people as well.
Oh, so from humans to horses,
and
now to humans.
And so human handlers, so vets or kids that handle horses, can become colonised. And it doesn't make them sick necessarily, they're just colonised. But if they happen to have to go to hospital and they're carrying methicillin-resistant Staph aureus, it can complicate treatments.
So what should horse owners, horse lovers, horse riders be aware of when it comes to resistance and bacteria?
Well, look, it's the same with all animal owners. It's hygiene, so it's washing your hands. And it's, and it's a bit hard to avoid getting up close and
Clearly not.
with horses. But if you reduce the bacterial exposure and contamination, you're going to reduce the antibiotic resistance.
But apart from our companions and pets, what of animals that we actually eat? There's now considerable evidence that we're exposed to resistant bacteria through the food chain, especially when meat isn't cooked properly.
There's a very nice study in the Netherlands where they showed that the chicken meat contained these resistant strains, contained these resistant genes, and that the humans who ate that, then their gut contained those resistance genes.
Professor Grayson believes his patient Ken Montgomery had a very similar experience. In 2012, Ken and his wife enjoyed a cycling holiday in Europe.
We flew into Paris and did a bike and barge trip from Paris to Bruges. I was eating and drinking very well with lots of exercise and fresh air every day. Yeah, good fun.
On his return home, Ken had a medical procedure, a prostate biopsy, where a fine needle is put through the wall of the bowel.
So, of course, in doing that, there's always a risk that bowel germs can be spread into the prostate. And about 24 to 36 hours after the biopsy, he developed a very high fever, became extremely sick.
Well, I just had a really violent sort of food poisoning for me. It was both ends, so diarrhoea and vomiting, and I started to get chills.
It turned out that Ken had a superbug and the infection could kill him.
Almost certainly that superbug that he acquired in his gut was obtained from food consumed overseas while he was travelling. The Ken strain, that's an E. coli, that'll be that pink strain. This germ that he had, an E. coli, which is called an ESBL, extended spectrum beta-lactamase, which means that it's resistant to all the penicillin class of antibiotics. Everything that was developed since Florey, no good. Only one last drug called meropenem was available for use.
Fortunately for Ken, that last antibiotic saved his life. He's fully recovered from the infection, plus his biopsy was clear. But procedures at the Austin Hospital have now been changed so that return travellers are advised to delay non-urgent medical procedures.
Ken's story is really, really important, and it's why people, infectious disease physicians, are really starting to get scared about antibiotic resistance. Because in the past, antibiotic resistance was something we would think of with someone whose immune system was weak. But now we're seeing these infections occurring in otherwise healthy people. And the colours tell us what strains it's likely to be. So for instance,
Lindsay's hospital lab is finding more resistance than ever.
with E. coli, a very common germ, in the last 6 weeks we've had 44 patients with this in their blood, and of those, 4 of the 44, so roughly 10%, have been superbugs. Now 5 years ago we would never have seen that. So this has been a dramatic change.
When it comes to food in Australia, studies are more limited, but they do indicate that levels of resistant bacteria in locally produced chicken and pork aren't high. But what about the fresh foods we import?
We love our seafood, especially these Aussie tiger prawns. But surprisingly, the majority of seafood that Australians eat is not our seafood. In fact, we import about 2/3 of it from overseas, mostly from Asia.
I wouldn't buy prawns for my family from Southeast Asia
Because?
because I think the conditions that they're raised under are not good in terms of both disease organisms and antibiotic resistance.
Other countries, unfortunately, people are putting in very valuable compounds like fluoroquinolones into fish farms, which I think is just crazy.
We could do everything well here in Australia, we could be perfect. But, you know, if you've got food imports from overseas and you don't screen, then everything could be undone. And that's currently the situation.
Of all the seafood that's imported, about 5% is checked. This lab routinely tests for antibiotic residues, but not for resistant bacteria, because national food standards don't require it.
When you look at those results, you see quite clearly that antibiotics are being used in imported seafood products. And, you know, as night follows day, that tells you that there's going to be antibiotic resistance present.
Animals and humans aside, what about the transfer of resistance in agriculture between soil and plants? Over the past 40 years, bacterial resistance in agricultural soils has increased way beyond natural levels due to the addition of antibiotic-rich manure. As a keen gardener, I often buy manure from the side of the road.
It occurs to me, I don't know if the animals that made this manure were given antibiotics or not. So, by adding the manure to my compost, am I unwittingly transferring resistance genes to a family's food?
Antibiotic-resistant genes have been recognized as a new type of environmental contaminant. You can find maybe a very high similarity between soil antibiotic resistance genes and human antibiotic resistant genes. Yeah, that is the link between them.
This is emerging research with astounding implications. Our food bowls may be more saturated with resistance genes than we realised.
Animal manure has been recognized and a rich reservoir of antibiotic resistant genes. When you applied manure into soil, it can increase the occurrence of antibiotic resistant genes in the vegetables at harvest.
In Melbourne, Dr. Hung Wei Hu is investigating the pathways from soil to vegetables and fruit.
Because antibiotics resistance can transport from soil into the roots. Also, it can be transferred from the roots into the fruits.
The next crucial step, whether the resistance genes are transferred to us when we eat vegetables, has yet to be proven.
Definitely in future, it is very important to do in this area.
Hung-Wei says that composting manure should reduce the level of resistance genes, as bacteria adapted to life in the gut can survive only a few months in the soil. But it makes me wonder, if we're all swimming in the same gene pool as bacteria, what does that mean for our waterways? Dr. Simon Toes and his team find urban streams in Australia are contaminated with antibiotics that leak from wastewater drains and sewage systems.
Probably the most surprising thing that we found was that the high-level use antibiotics that we use in our society for illnesses are actually matching a lot with the high level of antibiotic resistance genes that match those antibiotics in the environmental water. We're finding a range of resistance genes to some of the beta-lactams. They're the common ones that often people get when they're at the doctor. Even some of the ones like the chloramphenicol, which are not used for humans much, but also more for animals, cats and dogs and the likes. Yeah, 7.1.
The fear is that creeks like this in residential areas could be reservoirs of genetic material that turns harmless native bacteria into pathogenic superbugs.
If they take up these antibiotic resistance genes and people are in this water and get a scratch or a cut, they can actually get an infection which may be very hard to treat.
But in a world where bacteria are increasingly resistant to our medicines, we can just turn to new drugs, right?
Well, no, because the cupboards are almost bare. In the last 50 years, only 2 novel antibiotics have been developed for human use.
The main reason is economics. Pharmaceutical companies don't see antibiotics as money spinners.
Antibiotics are spectacular drugs and very safe, but we only take them for 2 weeks. So the net economic value of an antibiotic is close to zero. So we need to change the economics of antibiotics.
So they come from all around the world.
Matt Cooper is spearheading that change. With the help of the Wellcome Trust, he's taking a novel approach. He's crowdsourcing, not for dollars, but for compounds, in the hunt for new antibiotics.
We're actually crowdsourcing molecules now. So these are potential new antibiotics and antimicrobials. And the issue is they're not in one spot. They're in India and China and Canada and Russia, all around the world. And if we screen all these different compounds around the world against these superbugs, perhaps together we can find a solution. So every one of these little holes and wells here is potentially a new antibiotic.
How many have you done so far?
Roughly 32,000 so far in the last 12 months.
What's your hit rate been?
Very good. We're about 40 times higher than the current process that's been used. And so far, in the first year, we've got about 128 potential candidate compounds. But actually, if we just get one, that's going to be a great success story.
But even with new antibiotics, we still need more targeted ways to treat infections that don't kill all the good bacteria as well. Therapies that are less disruptive to the ecosystem are now being explored. Phage therapy is a much more focused alternative because it uses viruses to hunt down specific bacteria that cause disease.
In this vial are hundreds of millions of viruses called bacteriophages. As the natural predators of bacteria, they can kill germs that antibiotics can't. And there's actually a lot of hope in this vial as well. If patients can be safely infected with the right phage, it could mean a therapy to beat antibiotic resistance.
Until very recently, phage therapy was only used in the Eastern Bloc countries, and then with little scientific evidence. This Australian research is changing that.
So you know the phage is working when this is what you see. So the clear spot showed how the bacteriophage has eaten up all the bacteria around it. And from the different concentrations, you can tell that it's quite effective because even at the lower concentration, you see some activity of the phage against the bacteria.
The first human phage trial in the West is underway here in Adelaide.
Any problems with the wash at all?
None at all.
No burning or
nothing?
No side effects from it?
Professor Wormald is hoping to find the answer for chronic sinusitis sufferers like Martin Darling.
It affects your life completely. It affects your work-life balance, everything, because of the headaches, ongoing sleep issues, waking during the night, snoring, which the wife is really happy about.
Despite surgery, Martin's sinus infection continued, and repeated courses of antibiotics just increased bacterial resistance.
What happens when you get chronic sinusitis is we get an overgrowth of one particular type of pathogenic bacteria. And that imbalance then results in the pathogenicity developing from that particular bacteria.
The advantage of using phage therapy is they hunt down that specific type of bacteria. The phage injects its DNA into the cell. As the DNA replicates, the bacterium is killed and releases more viruses, which then go and find others to infect.
All right, Martin, we're going to give you the last phage wash now.
So when all that particular type of bacteria has been eradicated, phage die because they can't infect other bacteria, they can't infect human cells, they can't do anything other than target that specific bacteria which it's been formulated against, which makes it a very focused and unique type of therapy.
After only a week at a low dose in the first phase of the trial, for Martin, it's looking good.
From the endoscopic point of view, there's a substantial improvement, 30 to 40% better.
So all those sinuses look really beautiful.
I certainly feel clearer at the moment. Headaches have subsided over this past week. So yeah, I think it's certainly getting improved.
However, at this stage, phage therapy is limited to easily accessible infections, like in the sinuses, and not deep infections of tissues or the bloodstream. But there's another therapy currently being trialled in mice that promises broader application. It very precisely removes resistant genes from bacteria altogether. It does this by replacing a resistant gene package, the plasmid, with a benign engineered one, through food. Amazingly, mice that were once resistant to antibiotics, after treatment, respond.
So you end up at the 3-week mark with a mouse that looks like it's never met antibiotics or antibiotic resistance. And then if that mouse had acute leukemia or a bone marrow transplant, you could use penicillin or anything in the cupboard, really, to treat the infection. Whereas only 3 weeks before, you would have been really scratching.
Therapies like these offer a future where we can cure infections without making the bacterial ecosystem more dangerous for us.
We have the tools coming to hand to manage that ecosystem effectively. I think we need to move quickly into that space, though, and stop trying to just stamp on the cockroach.
With international cooperation, there's still a chance we can reverse the evolution of antibiotic resistance.
This is a chemical warfare arms race with the bacteria. Bacteria have been here before us, they'll be here after we've gone. So we can't just stand still.
We can't just be waiting for new drug classes in the pipeline. If we keep using antibiotics the way we do now, in 5 or 10 years' time, we'll be having a conversation about, oh, wonder mice, and we thought it was fantastic, but we've got resistance to it now.
Wherever the resistance is coming from, hospitals, food, the environment, the urgent task right now is to bring our profligate use of antibiotics under control.
We can certainly extend the life of the ones we've got, and we can maybe preserve the life of the ones that are yet to come.